All right. Yesterday I was studying the neutron interferometry experiment again, where the silicone crystal is used to diffract a neutron so that it splits twice, and then the second time it splits, the two inner beams converge into the third silicone diffraction, and the north beam has a magnetic field applied that then causes an interference with the south neutron in the that's been split. And there's a physicist I've read before. He studied in Switzerland, and he has a Italian last name that I can't remember how to pronounce it, but I think it's something de Bianchi, and I'll link it in the description. And he explains in great detail. He says, if you take this experiment and you blow it up to the size of Europe, so that the silicone diffraction that splits the neutron is scaled up, so it's like hundreds of miles apart for each silicone diffraction plate. The actual size of the neutron would be 1 centimeter cubed, because normally the neutron's so tiny. So he's saying that this proves that when the silicone is diffracted through or the neutron is diffracted, then and the magnetic field has an interference, and it only returns, the spin only returns to itself after 720 degrees. This means that the inherent 1/2 spin of the neutron can never be seen, because it's inherently not a wave, nor is it a particle. And this is the crucial point about spin, that spin is neither a wave, because obviously if you have a 1-inch, you only have a 1 centimeter cubed interference wavelength of the neutron as a wave, and therefore when it's split, the only way to explain it would be if you think of the neutron as a composite particle that's made up of the different quarks, and because it's a composite particle, it can never, one quark can never be observed by itself. It has to always be observed with the other spin quarks. And so the emptiness of the matter is actually due to the kinetic energy as the binding energy, and not the momentum energy. And so therefore, it's just as Louis de Broglie explained, that the particle, the spin, is actually being guided from the future, because, as Louis de Broglie explained, the phase velocity is a relativistic quantum analysis, so that it's the speed of light squared divided by the velocity of the particle. And so when they use the silicone for the neutron, what they do is they slow the neutron way down, so the magnetic field can be manipulated to demonstrate the 4 pi spin of the neutron, so that it comes back to itself because a neutron has no charge, so the magnetic field is revealing the internal angular momentum or the intrinsic and angular momentum as the spin that's inherent. It's inherently non-spatial, as this researcher emphasizes. It's inherently non-local, and by non-local they mean it's non-spatial. And so what Yakir Aronharof's research group has demonstrated is that the non-locality is actually a reverse time guiding field, using the entangled weak measurements they're not just entangled, they're non-local because they're non-commutative. And so what this researcher is emphasizing is that he says you cannot have temporal permanence in quantum physics, because most of the time the particle, since it's inherently non-local due to 1/2 spin, it doesn't exist within space-time because it's actually non-spatial, and by being non-spatial, the time as a variable cannot exist. And in science, there's no absolute time due to relativity, but in quantum physics, the particle is indeterminate and therefore cannot be said to exist until the interaction with the measuring apparatus or the detector occurs, as collapsing the wave function of the probability as amplitude. And so the non-commutativity as non-locality exists before the probability as amplitude squared exists for the particle to exist. And therefore the particle exists in pure time as non-locality or non-commutative space-time frequency. And so the interference, normally the frequency is directly proportional to the momentum in quantum physics. So the Heisenberg uncertainty principle is based on the momentum from the interference beats, or the quantum beats, between the location as the particle and the momentum as the velocity, based on also the direction of the momentum as a vector in Hilbert space. So it's a complex three-dimensional vector. But in fact, the vector has to have the 720-degree spin before it can be observed. And in actuality, the vector has this non-commutative two-dimensional topology that's added to the three-dimensional space-time. So that means that it's actually a five-dimensional non-commutative time. It's a primordial time or primitive time, and that's what non-locality is. And this is what these neutron experiments prove, that the spin as non-locality is neither a wave nor a particle, and that this is the truth of reality, that it exists in the fifth dimension, and it only exists as the relativistic energy of light. So it's the super momentum of light, because since light has a zero rest mass, then all of matter exists as the super momentum of light that can, based on a negative frequency, that can never be seen or observed. And so it's beyond just relativity, and it's beyond just quantum physics as it's normally defined. And this is why Roger Penrose calls it asymmetric time as the secret of fundamental time, because it's a eternal harmonization from the future. And these neutron experiments were my own quantum mechanics professor, Herbert J. Ernstein. He was the first to conceptualize how this experiment would be devised in 1967. And as his paper went to publication, he learned about Yakir Aronov and Lenny Susskind. Lenny Susskind and Yakir Aronov came up with the same idea, and so they published it around the same time, but actually a little bit later than Herbert, my own physics professor. And then in 1980, the same physics professor, Herbert J. Ernstein, he co-authored a paper with Anton Zeilinger, who just got the Nobel Prize in physics, with two other scientists for working on Bell's inequality theorem. And so this experiment is tied tied together with Bell's inequality. And normally the probability of Bell's inequality is assuming this symmetry, because you have to have the 720 degree symmetry in order to observe the particle as being entangled with itself based on the spin. And so because it's entangled and it interferes with itself, therefore the neutron experiment is actually a type of Stern-Gerlach experiment, because this spin is manipulated through the longitudinal plane of the neutron in the magnetic field, and not the transverse plane as based on changing the velocity of the momentum. And this is all explained in detail by this Bianchi scientist, so I will link his research. And it's a super fascinating research, and I just want to congratulate Anton Zeilinger and my own physics professor, Herbert J. Bernstein, who also practices Buddhist meditation, and thank my professor, Herbert J. Bernstein, for conceptualizing this neutron test of spin, observing the spin for the very first time. Because neutron, since it doesn't have a charge, then you can see the spin through the magnetic field. And that's what it meant. This is what it means, that this Professor Bianchi explains what the spin actually really means, that it's neither a particle nor is it a wave. And so that's how it relates back to non-commutativity. And Professor Basil J. Hiley, he's going to talk about this more in his forthcoming paper about Alon Kahn's math, Alon Kahn, the mathematics. So thank you very much.